Hello, everybody. Welcome to Chloethedev Unfiltered. I'm adding a new playlist to my channel. It's going to be just called Security for now. I'm going to add to it later. Hopefully, I get into the kernel security track, and I'll be adding a lot of my live streams for the reading material there in this playlist. For now, I just want to take the security articles or papers that I read and put them in this playlist so I have a place to kind of go back to and remember what papers I read, what I thought about them, my notes, my commentary. Um, I don't do a very good job of linking things in the notes, so I'm gonna try and do better at that. But for now, I'm just gonna jump in. It's a pretty short article. It's an article from OpenZeppelin. Came out October 6th. Sorry, on the OpenZeppelin blog, and it's by Santiago. We're gonna try not to butcher the name here. Payadino. Santiago Payadino. I think that's how you say it. He's a lead developer at OpenZeppelin, and what this article is talking about is the state of smart contract upgrade. So, in the kernel security track, I'm going to be learning hopefully about Solidity and smart contract development and how to do it safely. Or continuing to learn that, and so I haven't really done much Solidity training or not coding at all for a while, a few months at least. But I haven't even looked at Solidity in at least a few weeks. So I'm gonna get looking at Solidity again and get through it all. So this is a report. It's a survey of the different Ethereum smart contract upgrade patterns and strategies from a technical viewpoint, plus a set of good practices and recommendations for upgrades, management, and governance. So let's say last year, I feel like the idea was, it's not upgrade contracts, upgradable contracts is not a good thing. And now I guess the idea is, okay, fine, people are going to use upgradable contracts. It's the norm now in a lot of projects. But how do you make sure you're upgrading your project safely is probably the viewpoint of this paper. So here's your table of contents, and let's continue. So what is a smart contract upgrade? Smart contract upgrades are not a new concept for Ethereum developers. One of the oldest upgrade patterns can be traced back to a gist by Nick Johnson from May 2016, 4 years ago at the time of this post, which is an eternity for a blockchain that is 5 years old. I would agree. Since then, there has been a lot of work and different implementations for smart contract upgrades. Upgrades have been used both as a safeguard for implementing a fixed in the event of a vulnerability. So you put a smart contract on mainnet, on the chain, on a blockchain Ethereum, and you realize, oh no, there's a bug. Well, instead of having everyone remove their funds, what if the attacker steals all the funds before you can do that? If you can upgrade the contract and fix that bug before it gets attacked, then no harm, no foul, and you can continue. As well as a means to iteratively develop a system by progressively adding new features. I think like Argent Wallet is probably a good example of this. They have a smart contract wallet, and they have a lot of complex features in the wallet. And if I as a user had to remove my funds every time a new upgrade came out, I would not use that wallet. But because they can upgrade the smart contracts and add small adjustments and upgrades over time, they're able to have a really robust system and gain funding over time and users and gain some network effect. However, there has also been a great deal of controversy around smart contract upgrades due to the technical complexities they introduce and the fact that they can be a threat for true decentralization. In this post, we will cover both of these concerns. We will go through different upgrade implementations, reviewing some successful examples in the wild, and discuss the pros and cons of each of them. Then we will review some good practices for governance and management to mitigate the centralization risk of adding an upgrade option to a system. So if you're going to add an upgrade option, how do you do it safely? How do you do it efficiently? Not efficiently, I guess, but to mitigate the risk of, upgrading can be an issue. And so if governance has control of upgrading and someone can attack governance, then maybe they can attack the entire protocol. Oh, just with a simple upgrade. Sorry, my back is killing me. Let's start by defining what we mean by a smart contract upgrade. What is a smart contract upgrade? A smart contract upgrade is an action that can arbitrarily change the code executed in an address while preserving storage and balance. But before we go in depth into upgrades, we will cover some strategies for altering a system without having to implement a full-blown upgrade. So before we even get there, we're going to go through some ways, and let's not worry about upgrades yet because that's complex and there's lots of attack vectors there. But what are some alternatives first? Brace yourselves. This is going to be a long post, so I thought I was going to only be like half an hour, but maybe it'll be longer than that. We'll see. Upgrade alternatives. There are many strategies for modifying a system without requiring a full upgrade. An easy solution is to change the system through a migration, deploying a new set of contracts, copying the necessary state from the old contracts to the new one, which can sometimes be done trustlessly. I guess it would be tough to, but you'd probably have to do some planning beforehand, and simply having the community start interacting with the new contracts by social convention. This is kind of the way I would say most projects back in the day would do things. Not as common now, I would suppose. But Uniswap did this, and I enjoy that way of doing things. The upgrade strategies listed in this section can be used to modify the system in predictable ways. Unlike upgrades, which are able to introduce new code with very few limitations. This allows for simpler controls to manage them and a more predictable behavior of the system in the face of a change. Let's go through some of these strategies. So you have parameters configuration. And I like this way of having some parameters you can edit, but not editing the entire contract. So an option so trivial that I was doubtful to include it in this list is simply tuning a set of parameters in your contracts. Which I know it's very simple, but something when I think about these things. A good example of this is MakerDAO's stability fee, which is a numeric value injected in a contract that changes the behavior of the system. So one little number change changes the entire way the system works. But that could be an attack vector for changing the number, but different point. This value is changed frequently, and the operation can be carried out with confidence since its implications are clear. However, it's important to understand how the system reacts to extreme values set in these parameters. Arbitrarily high or zero fees can drive a system to a halt, or even allow an attacker to steal all the funds. Where if you haven't tested zero, or you haven't tested a really, really high number and it causes rounding error, you could have a lot of issues. It is often a good idea to hard code in the contract a range of reasonable values for its parameters to safeguard. So this is where, maybe you haven't tested every single possible value, but maybe you've tested a lot of values, so you can have a range for all the values you've tested. And that's what you use for your version 1 of the contract. And then as you test, let's say, a ton of new values, maybe version 2 allows for a wider range of values that you've tested for. Contracts registry. Systems comprised of multiple contracts may rely on a central contracts registry. Whenever contract A needs to interact with B, it first queries the registry to obtain the address of B. So I need to know where to get addresses from. I'm going to go to this address on the blockchain to figure out, I need to go to this Uniswap. What's the address for Uniswap? The contract has it in there. Okay. By having a mutable registry, so this registry can change. So if Uniswap upgrades to version 3, instead of changing my entire algorithm, I just go into the smart contract, I change the parameter, I would assume, or change the contract in the contracts registry, and replace B with alternative inflation B prime, changing its behavior. Earlier versions of Aave used this pattern. However, this mechanism does not preserve the state of B when switching to B prime, which can be an issue if a manual migration is needed. Some versions of this pattern mitigate this by decoupling logic and storage contracts. Again, you have to have more contracts everywhere. So state is kept in a contract that's left unchanged, and it can only be modified by a contract with a business logic that can be changed as needed. So you're just kind of you're complicating it out even more. We'll go deeper into logic and storage separation later in the article, so we're going to go through it. Awesome. Another drawback of this pattern is that it also introduces additional complexity for external clients who would also need to call into the registry before interacting with the system, which, again, the whole idea for Ethereum or blockchain is its composability, and you kind of lose a lot of that when you make really complex systems. This can be mitigated by adding an external facade with an immutable interface, which takes care of managing the registry lookup. Okay, so I guess, yeah, you just kind of, as the, you take care of, you handle all the complexity and you bundle it in a nice package. That can be audited, I suppose, but that, creates a simple to use. It's not like Uniswap, I think, has a nice little router. So it's a really complex system, but they have a router that can access functions easily, and I think that's kind of similar to what we're talking about there. So, strategy pattern. The good old strategy pattern is an easy way for changing part of the code in a contract responsible for a specific feature. Instead of implementing a function in your contract to take care of a specific task, you call into a separate contract to take care of that. And by switching implementations of that contract, you can effectively switch between different strategies. A good example of this is Compound, which has different rate model implementations for calculating the interest rate, and its C token contract can switch between them. Very cool. So you can just switch between different contract strategies. This allows to easily roll out fixes or gas improvements on the rate calculation, knowing that the change is limited to that specific part of the system. Very cool. So you can kind of like create something and then, create changes just to one part of the system. And yeah, you might have to kind of change. It allows you to kind of just change modularly and slowly, I suppose. Of course, a malicious rate model implementation could be set to always revert and halt the system, or provide an arbitrarily high interest rate to a specific account. So a specific coin, I guess, could be edited and have a huge issue, but I guess you couldn't affect the entire system, which is kind of hard. I didn't know that Compound used that, so add a little bit of security there. Still, limiting the scope of changes in the system makes it easier to reason about them. I think that's very true. You want to keep things as simple as possible. Oh, no worries. I really enjoy doing them, and so I'm glad that people come in and learn a bit as I do it. Sorry I didn't see that comment until just now. I only have like a little bit of my screen showing the comments. Anyways, let's continue. Still, limiting the scope of changes in the system makes it easier to reason about them. Okay, pluggable modules. A more complex variant of the strategy pattern is that of pluggable modules, where each module can add new features to the contract. Okay, let's see. In this module, the main contract provides a set of core immutable features, okay, that makes sense, and allows new modules to be registered. These modules add new functions to be called by the core contract. This pattern is most common in wallets, such as Gnosis Safe or Instadap. Makes sense. So your core, I think actually this is what Argent would use actually, not what I said before. Because it kind of makes more sense where you'd have like your core functionality of your wallet when you sign up. So you sign up as a user, you get your address, you get certain things that aren't going to change, and then they could add new functions to what you're able to do in the contract, I would assume. But Gnosis Safe and Instadap do use it for sure, so when I say other things, don't worry about what I say because I'm saying random stuff. Keep in mind that this pattern requires that the core contract is bug-free, right? Because any errors in the core Argent or core Gnosis contract, and you can't fix it, you can't upgrade it, the core contract needs to be bug-free. Any errors on module management itself cannot be patched by adding new modules in the scheme. Also, depending on the implementation, new modules may have the right to run any code on behalf of the core contract via the use of delegate calls, explained below. So they should be carefully reviewed as well. So again, any new code added to a smart connected to a smart contract, be very careful because if you're using, delegate calls and stuff. Anyways, okay. Now we're getting to delegate calls, which are kind of complicated, but it looks like they break it down pretty well through here. And there's an Ethernaut level walkthrough, which I've done. The Ethernaut is amazing. So if you want to go through Ethernaut, it's right here, the link. You should probably go through the entire thing. I haven't gone through. I'll go through it again because I haven't gone through it in a long time. and I'll probably go through it live. I'll probably live stream it, or myself going through it and fumbling through it before I do a security track, if I do it, because I learned a lot when I did it and I forget almost all of it. Anyways, upgrade patterns. After that not so brief introduction, it's time to go into actual contract upgrade patterns. Most of these patterns depend on an EVM primitive, the delegate call opcode. So let's start with a brief overview of how it works. Okay, so now we're going to go through delegate calls. It's an opcode in Ethereum, the EVM, that allows you to be able to do this kind of stuff. So in a regular call, okay, from contract A to contract B, so you have two contracts, A and B, you're making a call from one contract to another. Contract A sends a data payload to B. Super simple. We're calling, we're sending a data payload. Contract B executes its code in response to the payload. So you call and it responds, potentially reading or writing from its own storage, and returns a response to A. So A calls B, B gets that data that A calls with, and responds with does something and then responds, right? While B executes its code, it can access information on the call itself, okay? So here you go. A call from A, B picks up and gets some information. B can access the information on the call, right? That makes sense. A is talking to the phone, B is picking up and hearing stuff. B is gonna listen, do some stuff, but B has information that it can listen to. That's a normal call. That makes sense. We're all used to calling. I mean, most of us, right, on the phone and all that. Normal call between contract A and contract B. However, on a delegate call, okay, while the code executed is that of contract B, okay, so contract B is still, the code is executing there. Execution happens in the context of contract A, okay? So A is calling and making that kind of execution, but the code X being executed is from B. So it's almost like you're calling into something and using that thing to make executions from yourself. Anyways, this means that any reads or writes to storage that affect the storage of A, not B. So you're calling data, you're calling functions for data from B, but the read or write, the storage is affecting A. Interesting stuff. Also, message sender is set to the address who had called A in the first place. Okay? So now we're getting kind of like abstracting off a little bit. All in all, this opcode allows a contract to execute code from another contract. So like allows contract A to execute code from contract B as if it were calling an internal function, right? Because usually you can only call functions from other contracts if it's an external function, externally calling, yeah. But you're calling it as if it was an internal function. This is what powers Solidity external libraries under the hood. Okay. For more information on how delegate call works, you can look into it more. It's no matter how many times I read through this and I understand it, it is very, very complicated when you actually get code. It is very, very complicated to actually work through it. So I would definitely suggest going through this F9. You know what? I'm just gonna click it. Oh, I didn't mean to click it on the same tab, but I already did it. So let's go back. But I'm gonna add this to the notes. So we're gonna go to Ethernaut level 6, I think it is. Oops. Perfect. Save. Now it's in the notes, and now I can remember which one I should go do later. Anyways, now proxies and implementations. Delegate calls open the door to the proxy pattern and its many variants. First popularized in Zeppelin OS and Aragon OS, I strongly recommend this post. First popularized in by Gnosis's Alan Liu, if you want to go in depth on delegate proxy contracts technical details, maybe eventually, not today. At its most basic level, this pattern relies on a proxy contract and an implementation contract, also called a logic contract or a delegate target. The proxy knows the implementation contract address and delegate all calls it receives to it. Okay, so this proxy knows some address of a delegate contract and says, you know what, all calls we receive, we're going to delegate it that way. So this is sample code. Do not use it in production. So you have a contract called proxy. It's going to have an address, which will be the implementation address. So I guess that's going to be the address of the logic. They're going to have a fallback function. So any calls that come to it from an external function, even if you're sending ether, it's going to return implementation, right? So it's going to return this address, so this logic address, and then delegate call with the value, the message value, message data. So all the ETH, all the data, everything will be called, I would assume, I think that's what it says. Now, if I'm wrong, come look at yourself, tell me I'm wrong, because, you know, I haven't looked at Solidity in a long time. Since the proxy uses the delegate call into the implementation as if it were running the implementation's code as its own, it modifies its own storage and balance and preserves the original message sender of the call. Users always interact with the proxy and are oblivious to the backing implementation contract. Okay? So basically, this just means that the message sender, so you as someone using this contract, you are calling it, right? But you don't really know where the logic is being called from. You just know what you're calling in the original contract. And that logic on the back end could be changed at any point in time and you wouldn't really know, which is kind of the issue of all this stuff. Yeah, you call, then it goes to the proxy contract. The proxy contract delegates all those calls to the implementation contract. Executing an upgrade is then straightforward. By changing the implementation's address in the proxy, the proxy contract will then use whatever logic is on the new address you've given it. It is possible to change the code run upon every call to it. While the address the user interacts with is always the same, state is also preserved since it is kept. So all the state is kept in the proxy storage and not that of the implementation contract. So as you change the implementation contract, as you change the logic, it doesn't really matter to, security-wise it matters, but state is preserved in that original proxy contract. So how much ether balance you have, how much token balance you have, all that is probably kept in your proxy contract, and these implementation contracts for logic are probably upgraded over time to add new logic to whatever you're using. Oh gosh, so many, okay. This pattern has another advantage. A simple implementation contract can serve multiple proxies. Since storage is kept in each proxy, the implementation contract is only used for its code. That's actually very cool. Each user can deploy their own proxy, and people can kind of go to those and point to the same immutable implementation. I think that's super cool because this is where you start getting composability, right? Where you have, one entity can just worry about a proxy contract and getting a bunch of users and do things in one way, and people can trust that proxy and trust holding their state with that entity. But different smaller companies can work on really cool implementation details that get fully vetted and fully audited, and then a bunch of companies can be like, hey, you know what? We trust this implementation logic. Let's all point to it for now. And people can point different parts of their logic to different implementation contracts at different points in time. However, there's a missing piece. We need to define how the upgrade logic is implemented, and this decision opens up the door to different proxy variants. Important stuff here. So, upgrading the contract is usually handled by a function that modifies the implementation contract. In some variants of the pattern, this function is coded into the proxy directly and restricted to be called only by an administrator. Okay, so I didn't even read that properly. Upgrading the contract is usually handled by a function that modifies. Okay, so you have a contract called admin upgradable proxy. So this is a proxy contract. Then you're going to have an address in storage for implementation, and an address for your admin, right? So if you're putting up this contract, you'd probably be admin. So if you're using your ledger or whatever keys you're using, that would be the admin. Let's assume. Okay. So anything called here, right? Externally, even if you use funds, right? You can use an ETH, doesn't matter. It's going to go to this implementation address in this contract, and it's going to delegate call, the value of the thing, the data, and it's just going to use that. Then when you want to actually call the function to upgrade, okay, it's going to take an address, the new implementation, which is what it's going to be, and it can only be called externally, fine, whatever. And then you're going to require that message sender, whoever's calling this, equals the admin. So going to equal your address because you put up this. And I guess arguably you could have that admin equal anybody. You could have it be a Gnosis smart contract wallet so that, you could have, voting based on who. Okay, it doesn't. But the point is, that's how it gets done. This version usually also includes functions to transfer ownership of the proxy to a different address. Makes sense. Compound uses this pattern with an extra twist. Ooh, so if you want to learn about extra twist, click that. The new implementation needs to accept the transfer to prevent accidental upgrades to invalid contracts. Very, very cool. So let's say someone happened to do a typo, right? And you say, okay, you know what, we're going to put this new contract in, but somehow your cat walks across your keyboard and then just puts a 0 in there, or puts an extra thing, or backspaces, or whatever. Instead of you losing, millions, billions, who knows how much money you might lose from doing a wrong implementation upgrade, because you could always fix it, right? But it might take a whole new vote and all this other stuff to upgrade these things. So with this, the idea is that you do the upgrade, but it'll revert. It won't work unless the new implementation accepts the transfer. And maybe it's an automatic acceptance that you've already coded into this implementation contract. But it will not work if it goes to a random thing. It won't work if it goes to a 0 address. And so a great way to add some extra security without adding too much extra complexity. This pattern has the benefit that all logic related to upgrades is contained in the proxy. And the implementation contract does not need any special logic to act as a delegation target, except for a few exceptions listed in implementation contract limitations and initializers. However, this pattern implementation, as is subject to a vulnerability caused by function selector clashes. Ooh. Okay, selector clashes and transparent proxies. All function calls in Ethereum are identified by the first 4 bytes of the data payload, which is known as the function selector. The selector is calculated from a hash of the function name and its signature. So now 4 bytes is not a lot of entropy, agreed, which means that there is potential for clashing between 2 functions. 2 different functions with different names may end up having the same selector. If you happen to stumble upon a case, the Solidity compiler will be smart enough to let you know and refuse to compile a contract with 2 different functions with different names that are the same 4-byte identifier. So this is where the Solidity compiler will stop you from making a mistake in the same contract, but the issue is possible, right, in Solidity in general. However, it is perfectly possible for an implementation contract to have a function that has the same 4-byte identifier as the proxy's upgrade function. So again, the compiler will stop you from making mistakes within one contract, but it can't stop you from making mistakes across multiple contracts. And so it's something to watch out for. This could cause an admin to inadvertently upgrade a proxy to a random address while attempting to call a completely different function provided by the implementation. So I was saying your cat walks across your keyboard, and I know those are kind of silly examples, but there you go. They're, select, and I use silly examples all the time, but I think this is why I like reading these papers, because now I can say, okay, there could be a selector crash, and there could be, a random address chosen, because of that function call, put some random data in there. This post explains the vulnerability, and someone else shows how it can be used for evil. All those papers both seem very fun. I will continue reading. This post seems long enough, honestly. However, this issue can be solved either by appropriate tooling while developing upgradable smart contracts or at the proxies themselves. In particular, if the proxy is set up such that the admin can only call upgrade management functions and all other users can only call functions of the implementation contract, clashes are not possible. Wait a second, let me read that again. In particular, if the proxy is set up so that the admin can only call upgrade management functions, isn't that always how it is? I'm not sure why there'd be no clashes possible, but I'm sure if I read these posts here, I'd probably learn that. But let's just read this. So contract, transparent admin, upgradable proxy. So here's your proxy contract. Oh man, getting tired. It's already 2:30. Jeez. Address, admin, fallback. So anything that goes in, okay. And then, so any functions, so any calls that come to this proxy contract wait. So this pattern is deemed the transparent proxy contract, not to be confused with EIP 1538, and is well explained in this post. Yeah, okay. This is the pattern used today by OpenZeppelin upgrades, formerly known as OpenZeppelin OS. Okay, and by extension by several projects in the wild. It is often used in conjunction with the proxy admin contract to allow admin EOAs to still interact with their own contract, since the admin can only manage the proxy. Okay, so now only the admin can, that's how you'd want it no matter what. Anyway, so it looks like you have to have an admin to stop this issue of selector clashes. Having an admin seems like a good idea, but then you got to secure your admin. But let's keep going. Let's see how this works in an example. Assume a proxy with an owner getter and an upgrade to function that delegates calls to an ERC20 contract that has an owner, getter, and a transfer function. The following table covers all resulting scenarios. So you have your message sender being admin. It returns proxy owner, and what it'll do is it'll upgrade the proxy, and if you try and transfer, it'll revert. But why can't the admin use the transfer function? I don't get that. I don't get why this would revert. So some other account, okay, if you call owner, oh, I guess this is on the other contract. I'm guessing this is the implementation yeah, this is the delegate contract. If you call owner, it'll return the owner of the account. If you call upgrade, it'll revert. That makes sense. So admin can't send? Oh. This is why they often use it in conjunction with proxy admin to allow admin EOAs to still interact with their own contracts since the admin can only manage. So it will revert unless you use the proxy admin contract. I get it now. Okay, hundreds of projects use this pattern for upgradability, such as DYDX, Pooled Together USDC, Paxos, Aztec, and Unlock. However, the transparent pattern has a downside, gas cost. Each call requires an additional read from storage to load the admin address, which became more expensive after the Istanbul fork last year. Furthermore, the contract itself is expensive to deploy compared to other proxies at over 700,000 gas. That's insane. First of all, not out of this, not like, geez, 700,000 gas. Doable, I guess. I've called functions at like 900,000 gas before. Wait, I've called functions with like millions of gas, so I know what you're talking about. It's not that high. But I guess if everyone's calling it all the time, it's a lot. But anyways. Then you have universal upgradable proxies. And as an alternative to transparent proxies, EIP 1822 defines the universal upgradable proxy standard, or UUPS for short. This standard uses the same delegate call pattern, but places upgrade logic in the implementation contract instead of the proxy itself. Remember that since the proxy uses delegate calls, the implementation contract always writes to the proxy storage instead of its own implementation storage. And the implementation address is kept, the only thing that, the implementation address is kept in the proxy storage as well. Nothing prevents the implementation from actually providing the logic for modifying the proxy's implementation address. Very true. UUPS proposes that all implementation contracts extend from a base proxyable contract. All implementation contracts extend from a base proxyable contract, and then the implementation contracts upgrade the proxyable. That sounds very complicated. Okay, so you have a contract called UUPS proxy, and it has an address for implementation contract. Okay, yeah, same stuff there. Then you have your abstract. Okay, contract UUPS proxyable. Okay. Then you have an address for implementation, an address for admin, and you have a function called, you have your upgrade function, which takes an address for a new implementation called externally, and it's requiring your admin and change implementation. Okay, interesting. This approach has several benefits. First of all, by having all functions defined on, so I guess this is that implementation contract with the function. It can count on the Solidity compiler to check for any function selector clashes. Furthermore, the proxy is much smaller in size, making deployments cheaper. It also requires one less read from storage for every call, adding less overhead. But yeah, the disadvantage seems more interesting. If the proxy is upgraded to an implementation that fails to implement the upgradable functions, it becomes locked so that the implement to it. Okay, so if the proxy is upgraded to an implementation that fails to implement the upgradable functions, it becomes locked to that implementation and it is no longer possible to change it. Some developers prefer to keep upgradable logic immutable to prevent these issues. That makes sense. Because at least if you did that, you could know that there could be issues as you upgrade, but at least each upgrade, as long as you do it similarly, shouldn't have bugs. That's a complicated difference there, like just differentiating the two and why you'd use the two. Anyways, proxy storage classes and unstructured storage. In all the proxy pattern variants, the proxy pattern requires at least one state variable to hold the implementation contract address. By default, Solidity stores variables in the smart contract storage in order. Makes sense? The first variable declared goes to slot 0, the next to slot 1, and so forth. Mappings and dynamic size arrays are exceptions to this rule. Okay. This means that in the following contract, the implementation will be saved to the storage slot 0. Makes sense. There's only one storage slot. It goes to 0. Now, what happens if we use that proxy combined with the following seemingly innocuous implementation contract? Okay, so you have your contract box, you have your address, the address is public and it has some value with a public address on the blockchain. Then you have a function where you're going to set this value, right? You're going to set and you're taking a new value, and it's going to be public, and anyone can come set it and set the address. Value is now going to equal new value. Okay. Following Solidity storage layout rules, any calls to box.setValue, so calling the function setValue in the box contract, made through the proxy, okay, will store the new value. So this new value that you took in right here, it's gonna store it in storage slot 0. But keep in mind that since we're using the calls, the storage affected will be that of the proxy, okay? Not of the implementation contract. So calling box proxy, I would assume, right? Dot set value would accidentally overwrite this proxy's storage, okay? Because normally it would change the data in this contract, but it's actually changing the data in the original box contract, the proxy contract. And you definitely don't want that to happen. You don't want to overwrite data by accident. You don't do anything by accident on the blockchain. The easiest way around this is to have box declare a dummy variable first. This will push all variables of the contract one slot down, avoiding clashes. So you have your contract box again, and then you have an address implementation not used here. This is your dummy value. Okay, then you have your address public for value, and that's your actual value. So that when you change this, okay, you're gonna overwrite. Wait, let's see. Yeah, you have this extra variable and you can't reuse it because you're going to end up overwriting this, and you have these two. Anyways, let's see. While effective, this is the drawback of requiring all delegate target contracts to add this extra dummy variable. This limits reusability since a vanilla contract cannot be used and is as an implementation contract. It is also prone to errors since it's easy to forget to add that extra variable in your contracts. I would not want to use that. I'd forget for sure. I mean, you tested a bunch, but still. To avoid this issue, the unstructured storage pattern was introduced. This pattern mimics how Solidity handles mappings and dynamic size arrays. It stores the implementation address variable not in the first slots, but in an arbitrary slot in storage. This is the arbitrary slot in storage to be precise. Given the addressable storage of a contract is 2 to the power 256 in size, chances of a clash are effectively 0. So you got your proxy contract, you got your fallbacks, any functions called in externally, even with Ether, are going to do, you're going to have an address for implementation, and it's going to be put in this slot in storage. And then at this implementation contract, you're going to delegate call everything to that implementation contract. This way, the first slots of storage are used by the implementation contract business logic, is what you want, and the proxy uses higher slots to avoid any clashes. For tooling purposes, the slots used by delegate call proxies have been standardized in EIP 1967. This allows explorers such as Etherscan to easily identify these proxies, since any contract with an address-like value in that very specific slot will most likely be a proxy, and resolve the backing contract address. Very cool that Etherscan can now do that. When I first heard about that, I thought it was very interesting and very cool, and how this is why I think EIPs are so cool. They make Ethereum life more efficient. This pattern effectively solves any storage classing issue with the implementation contract, with no drawbacks except for the additional complexity in the proxy implementation. So I think this is the way that I think I've learned to handle the whole storage issue. But anyways, storage layout compatibility with append only and eternal storage. Okay, contract upgrades introduce another challenge with regards to storage. In this case, not between the proxy and the implementation, but between two different versions of the implementation. Let's suppose we have the following implementation contract deployed behind a proxy. So you have this is the implementation contract, owned box. It's going to have an owner. It's going to have, I guess, the number of your box. And then it's going to have a function called setValue. It's going to take in a number, and it's going to require that message.sender is the owner of this. Anyways, a few months later, a new developer comes along and introduces some changes to this contract. As part of the new changes, they decide to sort the state variables alphabetically, just because they want to, and upgrade the contract in production. I think this is saying that now it's going to overwrite number instead of owner. You're going to get an address instead of a number. Keep in mind how the Solidity compiler decides to map variables to the contract storage. It is based on the order in which the variables are declared. This means that after the upgrade, the value of number is now in the slot assigned to owner, and vice versa. So yeah, you get an address here and a number here, and that's not going to work out well. Let me get some water in me. This shows a major limitation of smart contract upgrades. While it's possible to arbitrarily change the code of a contract, only storage compatible changes can be done to its variables. Operations such as reordering variables, inserting new variables, changing the type of variable, or even changing the inheritance chain of a contract can potentially break storage. The only safe change is to append state variables after any existing ones. The OpenZeppelin upgrades documentation includes a comprehensive list of forbidden operations. I love it. And the OpenZeppelin upgrades plugins will automatically check for them during upgrades. I love that too. So you should definitely have those plugins so that it can just, because you don't want to have to remember every single thing they do. Let OpenZeppelin keep iterating over all of these wonderful things to do, and let the plugin tell you when you done something wrong. Read up about it, and you can keep it if you want to keep it, but at least read up about what they're telling you is wrong. A development practice to ensure that storage remains compatible across upgrades is to use append-only storage contracts. In this pattern, the storage is declared on a separate Solidity contract, which is only modified to append new variables, never delete. The implementation contracts then extend from this storage contract to access storage. This actually makes a lot of sense. To mitigate secure attack vectors and security issues. So you have a contract again, own box, but now this is just a storage contract. You're gonna have an address, internal, right? It should only be changed internally, so only this contract is gonna be able to probably change or add, I think, I would assume, or read. Anyways, you're gonna have the address for the owner, you're gonna have the number, storage as well. Then you're gonna have another contract, own box is own box storage. So own box is gonna use the storage here, and function set value. It's going to take in a number for new value, and it's going to require, first of all, that message sender equals owner, and so it'll check the value here for owner, and if it does, then this number here will equal the new value that you've taken in the function, and then it'll upgrade. Woohoo! The storage contract can then be extended every time it's needed to add a new state variable. Solidity guarantees that variables are laid out in storage depending on the order of the inheritance chain. So, extending them from the contract to add a new variable ensures that it will be appended after the existing one. So if you add a new variable, it will be added at the end of number. As an example, Compound uses this pattern for changes to their controller contract. That's awesome to know. I should probably look into Compound's contract and Uniswap's contracts very soon. I've been lazy, and honestly, DeFi contracts don't interest me that much. I'm actually very excited to look through Mintbase's new contracts in Rust, but Rust is hard. Okay, so you have the contract, own box storage, you have your address, your number, and then you have your upgrade, own box storage v2 is own box storage, and then you're gonna have two internal new number, and I would assume this v2 would become it would have address, number, and new number attached. This approach has a major drawback though. All contracts in the inheritance chain must follow this pattern to prevent mix-ups. This includes contracts from external libraries that define their own state. Append-only storage requires special care when dealing with base contracts in the inheritance chain. Let's take the following example. This is a long article. Lord help me. Let's keep going. I'm getting tired though. I'm proud of myself for not getting tired until now though, because usually when I sit in front of the computer and start reading an article, I just get instantly tired. But I don't want to break this up into two parts. Okay, 1 second. Let me just do that so I know where I am, and let's see how much longer we have. Oh dang, we actually are only halfway through, eh? How long have I gone live? An hour and a half. Oh no, I have to watch time. Sorry, it's been about an hour. Let's continue because I've been enjoying the paper so far, and so we're just gonna be from here. So, append-only storage requires special care when dealing with base contracts in the inheritance chain. Let's take the following example. You have your contract base, takes in a number, base 1, a number, base 2. You have your contract child is base. So you have your number, child 1, number, child 2, and child's going to inherit from base. So the Solidity compiler will lay out these variables in subsequent storage slots in the order, right? So base 1, base 2, child 1, child 2. That's what we just saw above here. We would get owner, number, and then this new number. Okay, this means that if we were to add a new state variable to base, it would take the place of child 1 here. Okay, this this makes it difficult to make any changes to extended contracts. Still, there's a way around this problem. We can reserve space for future state variables in the base contract by declaring dummy variables again. Declaring an unused variable in Solidity will not consume gas, but will push down the slot allocated for other variables in the contract. Yes, but then again, you're adding complexity to your contract where you might know what's going on. And I guess if you put comments in your code very clearly, people would know what you're doing here. The upgrade safe fork of OpenZeppelin contracts uses this pattern in all contracts of the library. A different pattern developed to address storage layout compatibility is the eternal storage pattern. This pattern uses the same strategy as unstructured storage, but for all variables of the implementation contract. This means that the implementation contract never declares any variables on its own, okay? But rather stores them in a mapping, which causes Solidity to save them in arbitrary positions in storage based on their assigned names. And okay, mappings are freaking complicated for me. I started learning programming with Solidity, so mappings, I didn't learn linked lists, I didn't learn any of that, any of those list things in C programming or any of that. Beforehand, I pretty much started with Solidity, so mappings were a bit complicated for me, but every time I have looked at managing state in Solidity so far, mappings has been by far the easiest way, and so I'm interested to see if it's also the most logical way here as well. Okay, so you have a contract, eternal storage, and you're going to have a mapping where you're going to map some bytes, some storage, some data of a number. Okay, so this number is going to get hashed to some bytes, string, address. Bytes can also get mapped, bool, and an int of 256. Okay, then you have your contract box is eternal storage. Okay, so it's going to inherit all of these variables, and then when you call the function set value, okay, it's going to go into storage right here, okay, regardless of where it, and it's going to change whatever value is in there, right, in this mapping, it's going to put this new value for this number that's being stored. Okay. As examples, Hyperbridge and Polymath use this pattern for their respective protocol contracts. While it guarantees no issues during upgrades, okay, which is a good thing, because that's a pretty, after we've read all these pages, in my opinion, this is a pretty strong certification to declare. It requires a major change in how all contracts are coded, incompatible with contracts that do not follow this convention, and produces far more awkward code. It's funny to me. This seems less awkward. Because unit storage was here, I knew exactly what I was looking for. Um, and I would know where this value was to look for in the original contract. And so, but obviously, people who are used to one way of doing things would call other things awkward because it's not what people are used to. I don't do this much, and so this looks normal to me. Using strings for identifying variables can also lead to errors due to typos, unless constants are used for the mapping keys. And that's where I think it would be a good idea to use constants for the mapping keys for sure, if you were going to continue upgrading in this way. There are also proposals to address this issue at the language level, such as allowing to specify the location of a variable. Under discussion since May 2016, or having a contract allocate its variables in slots computed from hashes of the variable names, as in internal storage, yes. Until these are implemented, the best options are still to heavily test upgrades and complement them with automated tools to validate the changes introduced. I really like this upgrade pattern, just using mappings and using eternal storage and all that, and just anyways. But I feel like I want to read a lot more about this. Geez, like where's? Yeah, sorry, I want to. Okay, yeah, there's a whole blog post on it, so I guess I'll go through it later. Or you know what? I'm just gonna take this link, and this is why I do this, and I'm gonna add this to my notes. Eternal storage, right? And now when I come back to this, I can go look at that upgrade pattern and learn something from that. Okay. Implementation, contract limitations, and initializers. Even under the unstructured proxy pattern, there are some limitations to the contracts that can be used as implementation contracts. These limitations are detailed in the OpenZeppelin upgrades documentation, but the most impactful one is not being able to use constructors. Okay. And solidity of the contract constructor is not part of the contract runtime code that gets deployed. It is actually code sent along with contract deployment, but that gets discarded after it's executed. So it runs one time on contract deployment, and then the code gets discarded. Thus, once the implementation contract has been created, there is no way to invoke its constructor code anymore. This means that proxies cannot call into the constructor to initialize their state. To work around this, constructors need to be changed into regular functions, usually called initializers. So instead of being a constructor where it only does something when the proxy is put up, it needs to be an initializer. It's a function that can be called whenever a new implementation contract is implemented. Since these are regular functions, they do get compiled into the contract and can be delegate called by the proxy to initialize it when it's deployed. However, since they are also regular functions, they need additional logic to ensure they can only be called once. Makes sense. So bool initialize, require not initialize, and then once you initialize it, you change that bool to true. And then if you tried to call it again, you'd require not initialized, but initialized will be true, so it'll be initialized and it won't let you do it. Cool. To facilitate this, OpenZeppelin contracts includes a base initializable contract that provides an initializer modifier that implements this pattern. Note that this also requires that any smart contract library dependency used also follows this pattern. This has led OpenZeppelin to maintain an upgrade-safe fork of the contracts library where constructors have been replaced by initializers. though we have been at work to remove the need for it in the near future. I want to read that, but I don't have time. So many articles, so many rabbit holes. Another practice is not allowing the self-destruct operation in implementation contracts. If a user accidentally calls into your implementation contract directly and happens to execute this function, the implementation contract will be destroyed. And all proxies will be left without their code, rendering them unusable. I think this happened a while ago. Some smart wallet, someone was poking around, not doing what it was supposed to, and called a self-destruct on a proxy. And would effectively brick all maybe this article here is talking about it. Yeah, the parody wallet hack. Yeah. That was not good. Lots and lots of money. Sorry, I didn't mean to do that. Lots and lots of money lost in that one. Okay, multiple implementation contracts with diamonds. In all proxy variants we've explored so far, each proxy is backed by a single implementation contract. However, it is possible for a single proxy to delegate to more than one contract. First explored as vtable upgradability in OpenZeppelin Labs, this pattern evolved until being standardized by Nick Mudge under the name of Diamond Contract in EIP 2535, currently in use by projects such as Names. In this version, instead of storing a single implementation address, the proxy stores a mapping from function selector to implementation address. When it receives a call, it looks up an internal mapping akin to a vtable used in dynamic dispatch to retrieve what logic contract provides an implementation for the requested function. That is cool. Okay, so it's just gonna map this to an address of 4 bytes. This pattern has a few advantages. To begin with, it allows going over the maximum contract size. Yeah, because you could just have a contract and have your implementation be on multiple contracts. Arguably, you could just never change those contracts and it could be immutable. It also allows for more granular upgrades, allowing to change only a particular function at a time. This is so cool because you can have your contract, and you can have arguably every single function going to a different contract, right? And then if you wanted to upgrade a certain function, just change one contract at a time to upgrade. That seems very cool. Okay. However, this flexibility comes with limitations. For one, having multiple implementation contracts, writing to the proxy storage can lead to storage clashes between the different implementations. You don't want that. This is solved in the Diamond proxy pattern by using a variant of unstructured storage, where each implementation's storage is defined as a struct and stored in an arbitrary storage position to avoid clashes. That's very smart. Still, if different implementations need to access the same storage, they would need to extend from the same base storage contract, which needs to be kept in sync among all deployed implementations. Oh my gosh. Smart contract security is complicated. This is why I haven't built anything. Build this so easy. Yeah, it's easy to fork someone's code, but just because I fork someone's code doesn't mean that they won't get bugs. So if I fork their code and they've been audited, but they're going to keep looking at their code and keep improving. And I have to then take that audited code and then keep improving, or else my code's going to be stale. And it is not that easy. Yep. This pattern also makes code reuse within the same contract more difficult. Auxiliary functions that are called from more than one implementation need to either be included in both via inheritance or be defined as a separate function in the vtable, which requires an external call instead of an internal one, requiring additional gas and permission checks. Gosh. On the other hand, this force split can help achieve good modularity and separation of concerns within the smart contract system. Upgrading is not easy. Okay, simultaneous upgrades with beacons. While multiple implementation contracts per proxy is definitely interesting, let's now discuss the opposite. Multiple proxies per implementation. I think this is potentially more realistic, like what we'll see in the wild, in my opinion. I'm not really sure. When we introduced the proxy pattern, we highlighted that a single logic contract can be used as implementation for several proxies, since each proxy holds its own state. However, in this situation, if we found a bug in our implementation and deployed a fix, we would have to individually upgrade each of our proxies. So here you're putting the burden of trust on the implementation and not really on the proxies to be, where where your trust is held, I suppose. Which can be cumbersome and expensive if we have several of them deployed. But I guess this is where you're always thinking it, right? Like, I don't know, anyways. Enter the beacon pattern. First introduced by, I guess, the Zero Age and the Dharma Smart Wallet. This pattern, each proxy holds the address not to its implementation contract, but to a beacon. Okay, so each proxy holds the address to a beacon. The beacon, in turn, holds the address of the implementation. Whenever the proxy receives a call, it asks the beacon for the current implementation to use. All proxies that share a beacon can be upgraded in a single transaction just by changing the address stored in the beacon. Right? Again, this seems like a pretty simple way of doing things. You kind of just say, before anything happens, check the address here for where to do all your logic from, and then I guess you could have multiple proxies all sharing the same implementation logic. And I wonder if in this sense, every single wallet is a proxy app. I'm not really sure. But here you'd have your proxy contract. There's going to be an address stored in the contract. Called beacon. If you write immutable like that, does it just become immutable? Maybe it does. I don't know. I can't remember. Is it a global variable like that? Anyways, fallback, variable, address implementation. We'll go to the beacon and dot implementation, and then return dot. And here's the implementation address here where you get it, right? So beacon, from beacon, get the implementation address. So here's the beacon. And there would be the implementation address. And then you're going to delegate everything to there. This pattern has another advantage. Proxies no longer need to keep anything on their own storage, removing the need for unstructured storage altogether. Since proxies always point to the same beacon, the other beacon address can be stored in code instead of storage. So the beacon address can be stored in code instead of storage, reducing gas costs. Right? So you're assuming your beacon address never changes. So you can hard code that into your proxy. Right? So you open up a proxy, which is your wallet, I assume, and you have your beacon. The beacon is what changes to know where your implementation is. And then you have your proxy, wallet, your address, and you go through whatever address the beacon tells you to go to, and you get all your logic from there. The beacon itself could also be designed to keep the implementation address in code, instead of storage by implementing it as a metaphoric contract. Yeah. Note that it's possible to combine both the traditional upgradable epoxy contract approach and the beacon approach by allowing the beacon itself to be changed. This allows the owner of a proxy to fork to a different beacon. However, this leads to higher gas costs, both in execution and deployment, and more attack vectors. I mean, the whole point, in my opinion, would be allowing a very few things to be upgradable to keep your project going, while still keeping most things immutable. Non-upgradable proxies with EIP 1167. While they have no place in an article about upgrades, it wouldn't be fair if we didn't mention non-upgradable proxies after dwelling so much on proxies. These proxies are known as minimal proxies and are standardized in EIP 1167. Why would we bother with proxies if not for upgrades? The answer is to reduce deployment costs when multiple instances of a contract are needed. Deploying several copies of a large contract can be very expensive in terms of gas costs. So it's more cost effective to deploy a single copy to act as an implementation contract and spawn multiple proxies backed by it. Now, if these proxies do not need to be upgraded, they do not need any storage management functions, making them dead simple. So yeah, I guess this would be where, in my opinion, if you wanted to like, I would only use this in my head to like practice upgrading a contract, where you'd have like your main logic and then proxies attached to it with differentiating logic that are a little bit like maybe like you have all the functions in your one contract, and then you have some proxies that only would use like parts of that maybe. But let's see. You have the contract, just minimal proxy, the fallback, external payable, and it's going to return whatever the implementation address is, and it's going to do everything there. In fact, these proxies are so simple that they can be implemented in just the following 45 bytes of assembly. Very cool. Oh man, I do want to deep dive into how this code works. Fine. I'm going to add this to my list as well because this seems like a very interesting article to read. So deep dive into minimal proxy. And so, maybe my next video tomorrow, maybe I'll go through some of these extra links that I've been going through, and that'll persist into this this playlist of like security type videos that I live stream through. Okay, abusing Create2 with metaphoric contracts. Now to wrap up this section, let's review one last pattern for upgrades presented by Zero Age under the name of metaphoric contracts. This pattern has a major difference with the ones reviewed so far. It preserves the contract address among upgrades, but not state, which technically breaks the definition of upgradability we gave at the beginning of this article. This significantly reduces the scenarios in which it can be deployed. However, it has some major advantages over the proxy patterns. This pattern relies on the Create2 opcode introduced in EIP 1014. This opcode makes it possible to manage the address in which a contract will be deployed. When a contract is deployed using Create2, its address is determined by the contract deployment code, the sender, and assault. So you have some random data, you have your contact code, the sender, and you kind of get this address. The original motivation for this opcode was its usage in counterfactual instantiation used in generalized state channels, but they were soon repurposed for upgradability as well. The trick lies in the fact that the deployment address is not calculated from the contract code, but from the contract deployment code. The deployment code is code that performs any necessarily initializations, i.e. runs the constructor and returns the contract code to be created usually hard-coded in it. However, the deployment code may also fetch the contract code from somewhere else, such as a mutable registry. Okay, very cool. This allows different code to be deployed to the same address by using the same factory contract and the same hash. So basically the idea is if you know the code and the salt and all that, then you could, copy the exact same address people trust with different code underneath. Combine this with the self-destruct opcode where you can delete everything that's there. That clears the contract code, and we have built ourselves a mechanism to change the code at an address. I wonder if I can use the self-destruct opcode on an NFT to get a refund. Right? Because the remaining ether stored is sent to a target and the storage and code is removed from the state. Removing the contract in theory sounds like a good idea, but it's dangerous and is as if someone sends ether to remove contracts lost forever. What I would like to do though is, I know you can get a refund for clearing out state on Ethereum just in the EVM, and so I know NFTs use state on Ethereum, and I know like NFT stores or contracts, and I know that you can burn NFTs and reduce the state. And so I wonder if burning an NFT would reduce enough state, or if you have to reduce an entire store. But if someone like had 3 mint-based stores or 3 stores on the blockchain for NFT construction, I wonder if deleting those stores, deleting the state, would give enough refund for the gas. I really want to figure this out. That's one of the products I want to work on. But anyways, note that this approach does not require a proxy contract to be used, nor does it require the contract to change its constructor to an initializer. It would be the ideal upgradability approach if it were not for a major drawback. Calling self-destruct not only wipes out the contract code, but also its state. Furthermore, self-destruct does not immediately clear the code. It only gets cleared at the end of a transaction. This means that an upgrade requires 2 transactions, one to delete the current contract and another to create a new one. Any transaction that arrives to our contract in between these 2 would fail, effectively introducing a downtime for our upgrades. That's fine. I mean, it's not that big of a deal, I guess. Still, there are situations where metaphoric contracts are still useful. Contracts that contain only logic, similar to Solidity external libraries, are the most obvious candidates. Another use are contracts with little state that changes infrequently, such as beacons. In these cases, state can be embedded into the code, making it cheaper to access it, and the contract can be upgraded whenever the state needs to be changed. And I think, that's a use case where people have, in my opinion, come to trust hard-coded, or people have already come to trust certain address and have already hard-coded it. And so it'll allow other users to continue to hard-code this address if you continue to say, you know what, we're going to keep using, create 2 and self-destruct to upgrade our contract, so you can hard-code into us. Okay, so now we're getting into governance. Upgrades governance. With the technical challenges of upgrades now behind us, it's time to focus on governance. By governance, we refer to how the decision of upgrading a smart contract is made, from centrally and immediately to by a single trusted party or via a voting process among all stakeholders. Governance is critical to upgrades. No matter how technically solid your upgrade solution is, without proper governance for your project, upgradability is fundamentally flawed. The promise of smart contracts and ultimately blockchain technology is that of trustlessness, which falls apart at the moment a developer can single-handedly change a system to rob all participants of their funds. Lack of proper governance schemes is what often leads to critics of upgradability to consider it a bug in smart contract systems. It's important to mention that there is no universal solution to governance. Different systems will require different schemes. For example, a token vesting contract where A grantor provides tokens to a grantee over time, could be managed by just the agreement of the two parties involved. If they both concur in making a change to the rules of the vesting contract, they should be free to do so. But more complex systems will require more complex solutions. Let's go through them. So, EOAs, externally owned accounts. EOAs are the most centralized option for managing upgrades. A single user with a single key has the power over the entire system. Needless to say, this is far from ideal. Not only does it put the fate of all users in a single party, but it's also a security risk. If the keys of the EOA are compromised, the entire system is at risk. Because of this, EOA should only be acceptable during development. That's what I do. I got my ledger where I do all my development stuff. Even in development, when I do a lot of like my testing on mainnet, which I guess it's expensive, I know. But I do it all as if as an EOA. And if my keys got compromised, the Marvin J Foundation and everything would be at risk, I suppose. And eventually, we will hopefully move on to a multi-sig. And what I'd like to do is just code my own multi-sig. I do have at least 2 keys that I feel pretty confident and I'm secure about. Maybe even, no. I have 2 keys that I'm pretty secure about right now. Potentially a 3rd key soon that I'll spin up. And so once I have 3 keys, I wouldn't mind spinning up a 2 or 3 multi-sig for my personal assets and doing things that way. But multi-sig wallet contracts are contracts with multiple owners that can execute arbitrary actions when a predefined number of owners are in agreement. So, like I said, if you have 3 wallets in the multi-signature, then you might just code in some logic that says, as long as 2 out of 3 suggest this, then it should be fine. What I kind of would like to do more is that I can send whatever I want, but let's say if I want to send over a certain if I want to send over a certain amount of ETH, or code some logic in where there's certain stoppages. So let's say I'm holding most of my assets in ETH, and then if I want to submit any transfer above a certain value, or in a certain amount of blocks, so I can send maybe let's say 10 ETH every 1,000 blocks, let's say. And let's say someone tried to hack in and do more, I wanted to do more, then maybe I would only need 2 of 3 SIGs to do that. Or if I tried to send a transaction, or if I submitted a transaction on chain, maybe it would be something like I have some time to shoot it down or something like that. I don't know. I'm not really sure, which is why I haven't coded my multi-sig yet, because I've coded a few multi-sigs for fun, different wallets for fun. But I haven't really thought through the logic that I would want to have my own wallet yet. So one day I will do that. And yes, I would also want a time lock in there as well. It's pretty basic. Multi-sig wallets are usually set up to manage large funds on behalf of a team, but also be set up as administrator of a system. This way, any changes to the system, whether they are setting a new fee or changing the code of the contract, need to be greenlit by several owners. To further foster decentralization, these owners can belong to different teams as long as they are trusted to go to the system. I'm mumbling a lot, but Kyber just did this. So Kyber has a DAO, and Kyber actually delegated a lot of their voting and their stake and their governance to a few projects in the community that were trusted stakeholders, different exchanges and such like that, they felt would be at the community calls and have, so they gave them more stake in the system in that sense. Note that a multi-sig could even be used by a single user. That's kind of what I'm planning on doing, where additional keys represent additional devices, so different hardware wallets that I would have. So for example, I have one hardware wallet now that I use for the foundation and my son, I guess. I have one wallet that I use for myself personally, and I'm going to buy a new one that I use for the foundation. And that way I'll have 3 different hardware wallets with 3 different keys, and that's when I'll start doing more of my signing. This makes multi-sigs a good option even for single-person teams, just for security purposes. I am a single-person team, I suppose, and so I definitely have been meaning to do a whole multi-sig. Right now, I just kind of separate out my assets so that, if one goes down, it doesn't all go down. But I need to do a better job with my OPSEC. All in all, multi-sigs can go a long way in the path to progressive decentralization. However, most projects eventually go into a scheme where the control is passed on to the community through voting rights. I personally, for the Marma J Foundation, we're never going to voting rights. It's just not going to happen. I am perfectly okay staying a relatively small team and trying to be as secure as possible. And with a time lock to, let's say, and I do think I'm going to put a time lock into most of my assets eventually. Just saying something simple along the lines of like, like if I died and if no one could ever access my keys, I would want like, I don't know. I gotta figure out the logic behind it, but like, I'd probably want like an institution that I trust to be around for a long time. I know it like sounds horrible, like the government or like some lawyer. Or right now, there's not really a good solution for this, but I would like it to go to an institution that I could trust long term to be there, which is kind of the whole idea of Ethereum, is that there isn't one like that, but I will figure out it eventually. Anyways, when we talk about time locks, we're referring to enforcing a time delay to every change that affects the system. And this, I think, is one of the best ways to ensure you're not getting hacked, is just add time locks to everything. Time is a great security measure. It's very annoying though. It's very, for example, even the fact that I have to take out my ledger and manually verify everything when I do things, it's time consuming, but it's in my opinion, it's worth it for the extra security. In a setup with multi-sig governance and time locks, each proposal does not get executed immediately once the approval threshold is reached, but there is a time delay of a few hours or more, typically days, until it comes into effect. For example, for instance, DYDX implements this pattern via modified Gnosis multi-sig contract. And so the idea here is that whatever upgrades you implement could have bugs in it, it could have issues. Someone could try and take over your governance system and then implement a really quick change. And if it has a 2 days before implementation, then it gives you 2 days to kind of withdraw or fix the bug or fix the attack or mitigate the attack, if anything. The purpose of time locks is to allow users to exit the system if they disagree with the proposed change, from a code upgrade to an increased protocol fee. Without this control in place, users need to trust not only the system, but also its administrators, since they could enact any change at any time without warning. So like, if you're an LP for Uniswap, and then Uniswap all of a sudden says, okay, we're going to upgrade to take all your money. I mean, if it was for the 2 day wait, you can withdraw before that protocol was upgraded or changed. However, time locks introduce an issue. While they are a good practice before introducing a modification in the mechanics of the system, they are a problem when the change introduced is meant to fix a crucial vulnerability. And I think there's some interesting things here. For example, maybe if you have like a 10-person multi-sig, maybe you'd have a time lock if you only had 60% of the vote for something. But if you had 9 out of 10 quorum on a vote or whatever it was, maybe the time lock wasn't as important. So maybe there's a certain level of severity of actions where it's like, okay, you know what? If we vote, and I think this is where you get into the pausable systems too. I think all of these, whether it's shutting down a contract, time locks, pausing a contract, maybe these things should have different levels of quorum. Where if we could reach consensus on upgrading by 51%, okay, then we'll upgrade in 2 days. If we get 80% and it's a security issue, maybe with certain different parameters, we can come to an agreement on how we upgrade in those settings. Pausable. We say a system is pausable when it can be set in a mode where all operations to it are frozen. For instance, okay, this is insane that people trust USDC even though it can be paused, which is insane. Okay, I don't want any kind of money that could be paused. Okay, that's just such a, I don't know. I'm gonna keep going. How you gonna pause my money though? How you gonna pause it? I'm trying to go buy something and USDC is paused? What do you mean an emergency? My lord. A pausing switch is a good safeguard that gives you and your team time to react upon an issue and program an upgrade to fix the vulnerability at hand. This holds regardless of having a time lock set up or not. Keep in mind that when faced with a critical issue in a smart contract system, you cannot take your servers offline until you diagnose the problem. A pause is definitely a great idea for a lot of applications. Your contracts are on the blockchain, and the blockchain keeps running no matter what you do. The rights to pause a system are usually centralized. This allows trusted developers in the team to halt operations, but not like change how much money you have, not withdraw for you, but they can pause it. And usually pauses are set to be limited in time. So maybe, developers have power to pause for 24 hours or something like that, or a day or two, whatever, to kind of assess the situation and kind of mitigate the risks. However, pausing needs to be limited in time. You do not want to have someone who can unilaterally keep a system on hold at ransom by keeping it perpetually paused. The time the system can be kept in pause should be limited to a few hours or days. Note that if not implemented carefully, pausing can negate the effects of a time lock. The administrator team could pause the system while they roll out an unpopular, if not malicious, upgrade, keeping the users hostage and unable to exit before the change hits. Whew, some scary stuff. This situation can be mitigated by introducing escape hatches. Okay, now we're going to get into escape hatches. We're almost done. Escape hatches. An escape hatch is a mechanism coded in the smart contracts that allow the users to exit the system. I love these, even when it's paused. What it means to exit the system will vary depending on the system itself. As an example, MakerDAO is an emergency shutdown mechanic that pauses the entire system while allowing users to extract their assets. This shutdown can be enacted either by a community vote, as most other correct changes in the system, or single-handedly by a trusted oracle, right? But everyone will get paid, so it's not that big of a deal. It would hurt the trusted party anyways. As another example, Dharma has a minimal wallet implementation that provides access to an escape hatch and can be rolled out in the event of a contingency. Okay. I'm not going to read into that right now. Escape hatches are the last resource for a user to leave the system. However, they need to be carefully implemented. A bug in the escape hatch mechanism itself can render the system helpless, while an attacker exploits it to drain its funds. Commit reveal upgrades. An alternative to the mechanisms of pausing with escape hatches is to use commit reveal upgrades. One of the issues of time-locked upgrades for fixing vulnerabilities is that it's typically easy to reverse engineer a fix to know the vulnerability it patches. This way, publishing a time-locked upgrade to be implemented in a few days, it's potentially signaling attackers that there's an issue to be exploited, and they are free to do so during the window of time. Alternatively, developers of the system can push a hidden upgrade. They do not disclose the code of the upgrade, but to a group of trusted security advisors who can publicly vouch for it. And they just create a proposal with a hash of the upgrade commit for phase. When the time lock period finishes, they actually reveal what the code was, the upgrade, and then apply it immediately. I think that's pretty cool. This mechanism is under discussion in the MakerDAO community under the name of Dark Spells. I love it, as every change proposal in the context of Maker is called a spell. Note, this mechanism only prevents from signaling the issue, but does not help if the vulnerability is already exploited. Honestly, any obscurity you can add, I'm not saying you lead by security by obscurity, but adding some extra obscurity to add security is not a bad thing in my opinion. Voting. The last step on the road to progressive decentralization is to grant your community voting rights to manage the governance of the system. This requires a way to represent voting power, which is usually done via governance tokens such as MKR and MakerDAO or Comp and Compound. Token holders can then use their tokens to vote for or against changes to the system. Many of the mechanisms listed above, pausing, escape hatches, and commit reveal, can be used in conjunction with voting as well. Note that voting inherently introduces a delay to executing changes, since setting up a proposal for voting usually requires it to stay open for several days to give time to all interested stakeholders to express their opinion. This means that a mechanism for rolling out critical fixes is usually needed in conjunction with voting, of course. Conclusion: upgrades are a powerful tool in smart contract systems, useful both for iterative development and for protecting users in the event of vulnerability. Usage of upgrades has become widespread in mainstream projects in the past few years, with many patterns being used to work out the challenges, both technical and social, that arise from them. At OpenZeppelin, we believe upgrades to be an integral part of the toolset of a smart contract developer, and we continue to work on open source solutions to make them more accessible and secure to use, as well as including more patterns to the ones we already support. Go to the OpenZeppelin community forum to join the discussion about upgrades and more. And then a bunch of references and community stuff that I'm not going to go through right now, but pretty good article. I have some more articles to go through from this article, which I guess is the point of going through these articles. And yeah, that's all for me. I'm probably just going to, actually I have no clue, probably snuggle with my puppy for a little bit before Bianca gets home. But thank you for everyone who kind of popped in. Thank you, Pickup Blocks, who, said thanks for the video streams. You're very welcome. I definitely do enjoy doing these streams, and so anyone who might have watched, anyone who came in, thank you so much for coming in. If you please read the article yourself, if you're a developer, you think it might be interesting to you, and I'll try my best to continue going through interesting articles and papers and all that kind of stuff to share with you all, I guess. That's all from me, Chloethedev, heading out for the day. I hope you're all having a